Welcome back. Find the probability that a hand of 5 cards containing contains 3 of one kind and 2 of another kind. Okay, this is a nice problem. You want probability that a hand of 5 cards contains 3 of one kind and 2 of another kind. 3 cards of one kind and 2 of another. Well, we want to choose 2 different kinds. 30 out of 13 kinds. Well, so you're choosing 2 from 13, but order matters because having 3 aces and 2 kings is different from having 3 kings and 2 aces. So order matters. That's why you use a permutation. Once you have number of ways of getting choosing 2 kinds in order, now we start choosing 3 cards of the first kind. That's choosing 3 from 4. Then you are choosing 2 cards from the second kind, choosing 2 from 4. So number of ways we draw 3 cards of one kind, 2 of another kind is permutation 13 choose 2, combination 4 choose 3, combination 4 choose 3. In all, I hope my calculation is correct, 3744. In contrast, choosing 5 cards from a standard deck of cards, it's simply random choice of 5 from 52. So that's combination and you get a certain number. So probability that a hand of 5 cards contains 3 cards of one kind, 2 of another is 3744 over all possible ways. All right. Next, from a bin containing 50 balls numbered 1 through 50, what is the probability that balls numbered 10, 3, 15, 29 and 30 are drawn in that order if the ball selected is not returned? So this is sampling without replacement. You are not returning the ball back. So this is called without replacement. So let's go in order. Probability that ball number 10 is drawn from 50 balls. Well, one particular ball from 50 balls, so 1 over 50. Now that this ball has been removed, only 49 are remaining. Probability that ball number 3 is drawn from these remaining 49. Well, you are again looking for one specific ball from 49. So it's 1 out of 49. Now that 2 balls have been removed, only 48 are remaining. You want to know what is the probability of getting exactly the ball numbered 15. Well, there is only one such ball out of 48, so 1 out of 48. 3 have been removed, so only 47 are remaining. What are the chances of obtaining ball number 29? 1 out of 47. 4 have been removed, only 46 are remaining. What's the probability of getting ball number 30? 1 out of 46. So the probability that balls number 10, 3, 15, 29 and 30 are drawn in order. 1 out of 50 times 1 out of 49 times 1 out of 48 times 1 out of 47 times 1 out of 46. This is without replacement. Suppose you are working with replacement. So the total number of balls never reduce because once you get a ball, you put it back in the mix. So you continue to have probability of 1 over 50 for each draw. So the probability that the balls number 10, 3, 15, 29 and 50 are drawn in order with replacement is 1 over 50 times 1 over 50 times 1 over 50 times 1. You understand? This is for ball number 10, replace it. This is for ball number 3, replace it. Number 15 and so on. All right. Probabilities of complements and unions of events. Let E be an event in a sample space S. Probability of the event E complement. It is called E complement. That is from S, remove E. The complement of E is given by probability of E complement is 1 minus probability of E. Well, this is straightforward. The cardinality of E complement is cardinality of the entire set S minus cardinality of E. Now you simply divide by cardinality of S. That gives you probability of E complement. This will be 1 minus this will be probability of E. Here is an example of how to use complements. A sequence of 10 bits is randomly generated. What is the probability that at least one of these bits is a 1? Well, you have a sequence of 10 bits. So you have the chances of number 1, the chances of no 1 is the same as obtaining all zeros. This is 1 out of 2 to the power 10. Where did this 2 to the power 10 come? A sequence of 10 bits. Well, each entry has two options, 1, 0. That's what a bit is, binary digit. So you're essentially looking at a string of length 10. How many such strings are available? 2 to the power 10. You don't want any 1 in your string. That is, you want all 0. So that's precisely one string out of 2 to the power 10. So probability of obtaining all zeros is 1 over 2 to the 10. Therefore, probability of obtaining at least one is probability, that's 100%, that's 1 minus no 1, that is all 0, 1 over 2 to the power 10. Here is an important theorem. Let E1, E2 be events in the sample space S. Then probability of E1 union E2 is probability of E1 plus probability of E2 minus probability of E1 intersection E2. Well, you know that the cardinality of E1 union E2 is cardinality of E1 plus cardinality of E2 minus cardinality of E1 intersection E2. This is simply set theory. Now divide throughout by a cardinality of S. Division, 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 division. Well, this is probability of E1 union E2. This is probability of E1. This is probability of E2 minus this is probability of E1 intersection E2. That's it. For example, what is the probability that a randomly selected integer selected from 1 through 100 is divisible by 3 or 7? 3 or 7. Between 1 and 100, the numbers between 1 and 100 divisible by 3 are 3, 6, 9, 12, all the way to 99. How many are these? These are 33 in number, you see. 3 times 1, 3 times 2, 3 times 3, all the way to 3 times 33. Another way of seeing this, 100 divided by 3 is 33 and a third. So that is the integer part. Those many multiples of 3 you will find. So what about 7? Well, same story. 7, 14, 21, and the last one before 100 is 98. Again, divide 100 by 7, you will get 14 and 2 sevens. That's the integer part. So 7 times 1, 7 times 2, 7 times 3, and that's 7 times 14. So how many numbers are here? Multiples of 7? 14. What about numbers divisible by both 3 and 7? Well, if you are divisible by both 3 and 7, you are divisible by 21. So which numbers between 1 and 100 are divisible by 21? 21, 42, 63, 84. That's it. After that is 105, which is beyond 100. So there are 4 numbers divisible by both 3 and 7. So that's your intersection. So probability that a randomly selected integer from 1 to 100 is divisible by 3 or 7. For 3, the probability is 33 out of 100. For 7, probability is 14 out of 100. And the intersection is 4 out of 100. So probability of getting a 3, multiple of 3, or probability of multiple of getting a multiple of 7 minus probability of getting a multiple of 21. You have to subtract, right? In all, this is the required probability, 43 over 100. Lastly, here is a beautiful probabilistic reasoning, the Monty Hall 3-door puzzle. Suppose you are a game show contestant. You have a chance to win a large prize. You are asked to select one of the 3 doors to open. The large prize is behind one of the 3 doors and the 2 other doors are losers. Once you select a door, the game show host, who knows what is behind each door, does the following. First, whether or not you selected the winning door, he opens one of the other 2 doors that he knows is a losing door. So you see, if you selected the winning door, both of the other doors are losing doors, so he will select at random. Now, then he asks you whether you would like to switch doors. Which strategy should you use? Should you change doors or keep your original selection? Or does it matter? Well, what if you chose right first? If you switch doors, then you lose. You see, that's the thinking. But what happens is the following. Probability of choosing the correct door in your very first attempt is 1/3 because there are 3 doors and only one is the correct door. So that's 1/3. On the other hand, the probability of choosing the loser door in your very first attempt is 2 out of 3 because 2 out of 3 doors are the loser doors. So probability of choosing the loser door is 2 out of 3. Now you don't know which one you chose. Now the host is opening a loser door from the remaining 2 doors. The host is opening a loser door. So you know that the remaining one is possibly the correct door, assuming you chose the loser door first. So question is, if you stayed with the original door, your probability of winning is only 1/3. But if you switch doors, your probability of winning is 2/3 because this is the chance of choosing the wrong door first. So it's better to switch the door. Okay. So that completes lesson 19 and that basically completes our course. We will continue with a new course in our next video. Until then, bye.